this. Get out of here. Whoops. All right. So I've got all my devices on Zoom here. Like boom, boom, boom. Yikes. All right. I tried to find a room for us to, because we talked about just tacking on the lab so that we'd have more time. There are no rooms to be found, I guess. I was hopeful because there's only, what, 10 and a half I can stand, right? So 10 of us. And so, so that was a little bit disappointing. They did say that they would be able to find a room if it was not during the regular hours, but I feel like you guys have been kind of pushed around so much that that's something that we can do, but for now, let's just leave things as they are. Doing that though, I will not be able to make it to the lab on the 31st, so next Friday. So there won't be a lab on the 31st. And what I kind of want to do for the labs anyways is just kind of optional work on stuff time. I'll be there. And so, because we're going to be baking in the lab material into the course anyways. And so this week, come to lab if you want. You don't have to. You're all adults. You can decide what to do. But because it's just the 50 minutes, it's like blink and you miss it. We can't really get much done in that time. But it might be nice to kind of keep working on what we're going to talk about today, that kind of thing. And so we will have lab this week, right on the 24th. But no lab on January 31st. So just a heads up. It's the only real one that I'm gonna, that I know I won't be able to make it to. And no one else really uses R, so who else can I ask to fill in? No, just take a break on January 31st. Okay. So, okay, last day we talked about chapter 1, right? So chapter 1 was just kind of reintroducing the idea of regression, right? Fitting a line of best fit, looking at the residuals, right? The residual plots and transformations, right? We talked about all those things. And so in chapter 2, can't remember what it's called. Probably something like analyzing or. Thank you. Inference for simple linear regression. So in regression, we can do inference. Did you guys get to do any inference on, so hypothesis testing, for example, or confidence intervals on the slope? Usually we do it for the slope in Stat 230. Yeah, you do a hypothesis test, sort of, maybe mentioned, yeah, mentioned it. So we're gonna look at that. Obviously, we're gonna use R to do it, right? And so we're just gonna talk about inference. Inference, remember, is just hypothesis testing and confidence intervals, right? So it's just the broad term for that. And so for linear regression, right, especially simple linear regression, we focus our analyses on the slope, right? Because well, the intercept is not that interesting, right? There are rare cases where it might be interesting, but in general, we care about the slope. And our hypothesis is going to be, is this slope different from 0, right? Remember, if you look at a straight line like this, right, slope would be 0. There's no rise here. And so, well, that's essentially saying there's no relationship here, right? I'm just going to draw a straight line across here. There's nothing happening. There's nothing that says a value of x on the lower end is going to be different or behave differently from a value of x on the upper end, right? And so in regression, if we had something like just kind of random scatter, right? No relationship here. Then we might fit a line of best fit like this. Right. Our line of best fit, right, or a regression line. The regression line has a slope of 0 if there is no relationship. If there is no relationship. So what we do, if we fit a model, right, a linear model, then we test to see if the slope is significantly different from 0. Meaning, well, if the null hypothesis is saying, no, there's no relationship between these two things, then the alternative hypothesis is saying that, yes, there is a relationship between these two things, right? And so we test, our null hypothesis is that beta 1, remember, our hypothesis is always about the population, right? So we're always talking about the Greek letters. So if the null hypothesis is that beta 1 equals 0, right? This is the same as saying we're assuming no relationship. Then our alternative hypothesis, I use H capital A. You can use H lowercase a, H1 if you want. What have you guys been using? Nice. So my alternative hypothesis is that beta 1 is not equal to 0. I can do one-sided tests, right? One-sided meaning I'm only concerned with one extreme of the outcome, right? Making it positive or negative, right? Beta 1 is less than 0. Then I suspect that there's a significantly negative relationship, right? Or if I suspect that there's a significant positive relationship, right, then beta 1 would be greater than 0. But for now, let's just stick to two-sided, right? But let's just make a note. If we suspect a specific direction, if we suspect a specific direction, oops. Direction for the slope. We can use a one-sided test. One-sided or one-tailed. Again, whichever, curious which one you've been using. One-sided or one-tailed? One-tailed. Okay, but no one's thrown off if I say one-sided, I think. Right. So we can use a one-sided test, like HA is that beta 1 is less than 0, or HA is that beta 1 is greater than 0. Right. One thing to keep in mind here is that the output that we're going to get, right, and so the output that we're going to get is a t statistic. And so that t is going to give us a p-value. The p-value is always going to be a two-sided, right? So if you need a one-sided p-value, you'd have to divide it by 2, but that's pretty standard. And so this is hard to say, our R output will produce two-sided p-values. Will produce two-sided p-values. So if we run a one-sided test, we need to divide the p-value for this one, I'm just going by what the textbook says.
Because in the formulas that we were using last semester, when we do a two sides, we multiply by 2. But I guess
yeah.
Just talking about
But that's, yeah, so the reason for that is because you were probably going from a one-sided. So if you're using tables, for example, did you guys use tables or did you just, okay. You can use R instead, right? But same thing. So if you use the tables, it's easier to find the one-sided, and then you multiply it by 2 to replicate it. And so R has already done that for you, so then you need to undo it if you want a one-sided. Yeah, cool. Okay, what did I want to do before I showed you some output so we could talk about it? Because we've waited long enough. I think it's time to see some R here. So, still jumping around. What I did was, oh, you don't need that, was I posted just a little bit of code. It's not beautiful or anything like that. Oh, it's still scrolling. There. The chapter 2 code. It's just code to get you started, right? And so I think if you click on it, it doesn't download. I think Moodle just can't handle it. So probably open it, copy and paste into an R file. And while you do that, I'm gonna get this guy going here. See how I can make this work. I called it chapter 2 code, and it should be in week 3. Okay. Participants and make host. Okay. Let's see here. You are the host now, it says. Or I wonder if I can just, if I can still be the host. I'm gonna try to stay the host, but then stop the sharing and then try to share from here. Really kind of tricky. Okay, sure. Share my whole desktop with you guys. Weird, why is it? Okay. Okay. Oh yeah, I can probably use this one. I know we all need plugins, right? Annabelle picked a good spot.
Yeah, anyway, I charge you.
Oh. Yeah, there's a plug in here. Oh. We can move the desk up. No, just sit there. All right. And you guys can probably use this one. I can rearrange. Okay. Looks like it's working. Looks like it's still recording. I don't know. We'll see. All right. So did I open it or did I not in this little guy here? I had to do an update because I was running a really old version of our studio. And so now I have dark and stormy night. And you guys have, what was it? Something of the toes? Yeah. So anyways, there shouldn't be any differences, but you can see. Hey, why is it not showing? Great. Connecting. Okay. It's quite a lag on this thing. What's the point of being wireless if it's way slower than being hooked up? Weird. Okay. So I just pasted it into, well, actually, I wrote it in a .r file, right? So basic. If you want to work in a markdown file, that's fine by me, right? Doesn't matter, right? So whatever you want to do with your code. But here is kind of everything that we need. First thing we're going to do is install the stat2 data package. And let's see if I can make this bigger here. It's only a little bit bigger. I can kind of maybe zoom in. How though? Can't. Okay. So I guess I ran install.packages, and then if you start typing stat2 data, it should come up. You can just auto-complete it with a tab. Okay. So we can run that, but because things are slow on my end and I already have it, I'm just going to comment it out. Okay. So I guess I didn't have that line in your code, but you can figure it out. Bless you. So the stat2 data package, once you've installed it, you have to run the library command so it knows what to do. And then, okay. I just got a notification, but it didn't show up on there, so phew. No, it's just my husband complaining, so. If you run the data command, I'm not sure how much of this have you guys done? Like have you used data from other packages, that kind of stuff? So if you run the data of, and then the book is going through all the examples with the Accord prices, right? So the Honda Accord for different years, right? The prices, and then we're trying to predict the price of the Honda Accord based off of the mileage. I think it's mileage, yeah, mileage. And so if you run that data of Accord price, and again, if you start typing data and then just start typing ACC, it should come up with Accord price as an option, and then you can just tab and autocomplete. Just so you guys know, right, I don't know, you guys are all familiar, but as long as the cursor is somewhere on the line that you want to run, you can just hit Control-Enter or Command-Enter, depending on what you're working on, right? And then it'll just transfer to the console. Okay. So now, after running that, you should have your data set in here, right? Your accord price, 30 observations of 3 variables. We can just kind of have a look and see in here, but sure enough, we've got age, we've got price, and we've got mileage. Okay.
Yeah, directly run.
There's something not
Did
working.
you load the library? Yeah. For me, it came up.
Oh, so yeah, so here if you go. So if you go, oops. Install packages. And then go to that. Yeah. Once it's, because it'll take for a little bit. Mostly just to show you what you can do, right? We get lazy, so I just decided to save the accord price because I don't want to type that every time, right? So I just saved it at ACC. Sometimes that bites me in the butt because I've saved it as something weird that I have to remember. But anyways, so now, unless you run that, you can change all my code and replace all the ACCs with accord price. Fine by me. See if I care. But now we've got this ACC. And from last day, right, we can visualize this relationship by doing a scatter plot histogram, a scatter plot, right? So if we're using the price as the response variable, which makes sense, right? How is the price affected by things like the age and the mileage of the car, right? And so the price doesn't affect the age or the mileage, right? And so it's the only logical response variable. There are scenarios, right, where it's not obvious which one's which. And so you would just kind of say, I'm going to use this as my response variable. So if you plot those, thinking about it. There. So now I've got the price against the mileage, and it looks like a linear relationship to me, right? There's no concerns about nonlinearity, so that's what we talked about last day. It looks like I could probably fit a line here, and it would do an okay job. So after checking linearity, right, that's when we're going to fit our model, and then we're going to check the model fit. Right? And so I'm going to build my mod 1, and you've got the code. So I use the tildes because I find that I can use them most of the time, right? Plot y tilde x. You could do plot x comma y. Right? Doesn't matter. But for the linear model, it needs the tilde, so I always do y tilde x. If I can zoom in here, which it seems I can't, right? Y tilde x is what I use. Sometimes, some commands you're allowed to use x comma y, and notice that we're just playing around in base R here, right? Base plots, no crazy ggplots here, because the whole idea is just to quickly be able to see what's happening, right? ggplot is for when you're making your report and you're making things look nice and you're producing something that you want to publish, right? Something that you want to show the world. This is just background stuff, so we're not going to waste any time. Right? You can change things like the limits, right? Let's call them the limits because the command is xlim and ylim, right? And you use, let's see here. If you wanted to specify the x-lim equals, then we concatenate, so C, and I want to go from 0 up to 200 instead. So I know it's really small, but you give it well, a list, I guess. Concatenate 0 to 200, and then run it again, and then it'll adjust it. So we can adjust the x limits, the y limits, which is pretty useful if you want to make plots that you want to compare right across. And so I'm going to remove this. Well, maybe not. Keep it in there, whatever. So now, just kind of showing you little quick things. May or may not know. I don't know. I don't know how much you know. So if we have to fit the linear model, we already did that last week. So the LM command, and I'm just going to call it mod 1. That's my go-to. Mod 1, mod 2, mod 3, and that's pretty typical. If there's something really special, right, mod underscore no outliers or something weird like that. So now I fit my model and I've got mod 1 in here. Right, so that's what I was saying last day was, okay, well, once we fit the model, then it actually gives me a lot of information, right? So it gives me the coefficients, it gives us the residuals, kind of ignoring some of the stuff, it gives us the fitted values. And so how we access those is going to be with the mod 1 $sign, right? Because now that's its own thing that we can pull out the residuals. And yeah, you can tack on the residuals onto your main data if you wanted to, if you had to, right? Usually we don't have to. And so first thing we can do is we can add the line of best fit to our plot. ABLine or ABLine, one thing to keep in mind is it'll just put the line on the most recent plot. Right? And so it doesn't care what plot it's putting it on. It's just going to put it on whatever plot is up here. Right? And so that's something to keep in mind. Make sure that you kind of keep your plot command and your ABLine command close in your code, right? Otherwise, you might be putting it on the wrong plot. Now let's look at the meat and potatoes here. If we look at the summary of mod 1, right, and I'll just kind of get this a little bit bigger here. Got a lot going on here. So what we're going to do today is just kind of break down and look at all these components, right? And just talk about what they all are. And so at first it just tells you, hey, this is the model that you're looking at right now, so that's not very interesting, right? It's the price against the mileage, fine. It's giving you a 5-number summary of the residuals. Remember, we have to, so one of our things that we have to check is that we have nearly normal residuals, right? And so our residuals should follow a normal distribution. And also, it's just nice to know that they're kind of centered on 0. They seem to run between -6.5 and positive 6.5, right? And so just kind of things like that. So not really important, just kind of good to know where it is. Plus, it's worse if you think about it. No, that's the worst. Then we've got the coefficients, right? Our coefficients are our B0s and our B1s, right? There are estimates for the slope and the intercept. And so here, for a simple regression, it tells you that, hey, here's the intercept, and here's the estimate of the intercept is 20.8096. So our B0, or B naught, would be 20.8096. The estimate for the mileage, well, it's just the coefficient of the mileage. And so that's saying that the slope is negative 0.1198. Pretty sure the mileage is in thousands, hundreds, maybe something like that. So we do have to keep track of units, but for now, let's just say that the slope, right, for each additional mileage, whatever it is, 100,000, whatever the units for the mileage are, right, the definition of the slope says that for each unit increase in X, right, in mileage, we're going to see a slope increase, in this case, a 0.1198 decrease, right, in the predicted value of the price. Right? How am I going to do this? I was going to write the notes, but it's so laggy when I switch back and forth.
So increase in price is decreasing the mileage.
Increase in mileage decreases the price, right? Because this is how the price is affected. So I will switch over here, and I'm just going to stop sharing for a little bit. I wish it was a little bit taller. I wish I was a baller. Okay. So, what? For the accord price linear model, we've come to a spot where if someone's looking at the notes later, they will not make sense. It's like, oh, we did a ton of stuff in between there. But I guess there's the video. So the accord price linear model says that, okay, well, just to write it out kind of how it says, intercept like this, and let's see if I can pull it up here. And the ACC mileage, they have estimates of 20.8096 and negative 0.1198. Therefore, we can write that the price at, right, the predicted value of the price is, I'll do beta naught plus beta 1, and then X is the mileage. So if we replace these, then we've got the price hat is beta naught, oops, is the 20.8096, and then plus the slope, but the slope is negative, so I'm just going to write minus 0.1198. Keeps doing weird stuff here. Times the mileage. And let's just have a look here. I can't remember. I think it's in mileage is in, where does it introduce it here? Thousands of miles. And the price is also in thousands. In thousands, oops, not the slope, the mileage is also in thousands. So if I say the mileage is 50, what I actually mean is 50,000. Right. There? More? Oh, here. Sorry. It's just lagging. Sorry. Come on. Man, this is annoying. Come on. Where did you finish? I'll read them to you. Aha, now we're up. It's going to take me a while to get back there. So we do have to keep track of the units, right? Because that's going to affect how we interpret this line, right? For every mile that we drive, the price is going to increase. No, that's not how it works, right? Because we're talking in thousands. Since you have your output in front of you, I won't pull it up here because we're working on that, but you also have the standard error of the estimate, right? The standard error of the intercept and the standard error of the slope. So remember that if you're calculating t, right, then you've got your estimate over the standard error of the estimate. And so that's where that t, the t value in the output comes from. It's just taking the estimate divided by the standard error of that estimate. And then the next column is the probability that the absolute value of t is greater than that number, the number that we found. That's just your p-value, right? And so,
What does the 3 asterisks mean?
I'll let you finish. So underneath, it says signif.codes. And so if there's 3 stars, then it's just saying, cool. Then it's just, let me go back there. Stop sharing, okay. Start sharing, okay. Okay, so here, this looks bad, but it's actually just giving you a legend for interpreting the p-values. You don't even need it, right? And so it's saying if there's 3 stars, then the p-value is approximately 0. One thing that probably Claude really hammered home as well is that the p-value cannot be 0. There's always a probability of something happening, right? And so that's why it's really important that we say approximately 0, right? And so if it's approximately 0, it'll put 3 stars beside it, right? Reject the null hypothesis, whatever you do, right? 2 stars, the p-value's approximately 0.001. 1 star, 0.01, just the period, 0.05, nothing, 0.1 to 1. So it's just helping you read the p-values. But if you get to which I think is kind of funny, because if you get to the point where you're producing this output and you're trying to read it, you probably know what p-values are, right? And that they help you reject the null hypothesis. Typically anything smaller than 0.05, you have enough evidence to reject H0. And so these are all really small. So for the intercept, which we're not really going to be interested in doing hypothesis testing about, even though we can, right? The intercept is significant, okay? Meaning, oh, we need this intercept to draw this line. Makes sense. And, the mileage, right? So this is our explanatory variable or predictor. well, we've got this estimate, and now we want to know, okay, well, this estimate for the slope, what does it tell us about the population slope, right? Our beta 1, how far is it from 0? If our beta 1 is significantly different from 0, you're going to have a small p-value here, which we do in this case, right? And so how it works is it calculates your t. Oh, here we go again. You know what? We could do it by accessing all the little things inside the table. I think you do mod 1 square bracket, and then it'll treat it like a matrix. Anyways, let's just do it like this. Back and forth, back and forth. Oops. The t value, okay, now it's keeping up, sort of. The t value in the output is the estimate well, I guess it applies to both over the standard error of that estimate. So what we get, right, is t is, oh, lost it here. Hopefully it works out. Negative 0.1198 divided by the standard error of the slope, which is 0.0141. Just gotta make sure, I guess. You can use R as your calculator, 0.1198 divided by 0.0141. Phew. I get T is roughly equal to negative 0.84964533901. You have a T of negative 8.5, rounded to 2 decimal places. That's fine. But I like making the connection of calculating a T by hand and seeing it on your output, right? Because if we're used to doing it by hand, which you probably are, right? Next step would be to go to the T table, right? And so if you're using T tables, do you guys use T tables as well? Yeah. Okay. So then, so now if we have a T, then we know what to do with that, right? Here, the output just gives us the p-value, so we don't need to use the T table. P's, T's, yikes, right? And so now, if we use the T table, the T table doesn't say, but we would have n-1 degrees of freedom, right? And so, so if we use the T table with n-1 degrees of freedom, it's going to be different for the residuals, but for just both. They both have degrees of freedom. The T table. or is it n-2 because we're estimating, because the degrees of freedom, right? You just take your sample size minus the number of things that you're estimating. I guess we're estimating the slope and the intercept. I guess it would be 2. Not that it's going to make a huge difference. We do have -8, right? No t distribution is going to say that a -8 with 30 with a sample size of 30, regardless of if it's n-1 or n-2, is going to say that that's not significant, right? -8 is going to be significant regardless. In fact, my supervisor, he would just kind of use, well, bigger than 2, reject the null hypothesis, right? So we don't really need these p-values, right? We just need to say, well, if I am able to find a test statistic that's larger than 2, of course we have to take into account things like our sample size has to be large enough, right? And that kind of thing. But just as a rule of thumb, anything larger than 2, you're gonna reject H0, right? We just find the p-values or have the p-values from the output just so we can back it up, right? Well, I rejected because the p-value is smaller than this, right? And so, but just as a rule, anything beyond 2, right? A t of ±2, z of ±2, f's are different. They're different, right? But yeah. So if we use the t-table with n-2 degrees of freedom, we would find our p. This would be a one-sided p-value, but let's not get too bogged down here. Find our p-value is less than, and bless you, I don't even think there are any tables in here. So we shouldn't really be using them anymore. We don't need them. Did you have a t-table there?
I have Z and I.
Oh, it's okay. You've got all of them except for, that's fine. Less than, usually it's 0.005. Something like that. Oh. It goes to 0.005. Oh. Just 2 zeros. It's an itty bitty t-table. Now it's confirmed. Ditch one of those zeros. This is confirmed by the output that says that the p-value is 3.06 times 10 to the -9. Right? That's less than 0.005. I can promise you that. Right? And so this is confirmed by the output, which says the p-value is 3.06 times 10 to the -9. If you've shown me output, then of course you don't need to calculate the t's and use the t-table for the p-values because it's just given to you. I just want to make that link between what we have been doing and what we are doing now, right? There's no difference here. Okay. What does this mean? This means that our slope can be considered significantly different from 0, right? So therefore, we can conclude the slope of the line is significantly different from 0. Significantly different from 0. In other words, right, that means that there is a relationship here, and it's not just by chance, right? And so this means there is a relationship or you can say association too, between the price of a Honda Accord and its mileage. One thing that we have to remember, this data was presumably collected in a certain time period. Things change, right? A year later, this data might not be representative of the prices today, right? And so always underlying is that the data, right, that's what dictates when this prediction is reliable and all that kind of stuff. And so in the, I want to say not just the time frame, but same constraints as the data was collected under. Does that kind of make sense? Right, so under all the same conditions, right, in the same time, on the same website, on the same whatever, right, because I think it's from cars.com or something, there's a blurb in the textbook, but, right, so, as long, let's see how this works out, as the sample can still be considered representative of the population. How about we say that? As long as the sample can still be considered representative of the population. Ugh. Just sit back, enjoy the show. Come on.
Is there a general rule in statistics where if you do analysis, let's say 1 year data or data from previous year, or it's still adding?
Yeah, you would have to argue your way there, right? You would have to argue that it's still valid, right? There's no reason. So usually we say, oh, there's no reason to think that this would have changed, right? Oh man. But there's no rules. Usually, as long as we argue it, kind of do some weird stuff. But you have to argue it. What is going on here? Okay. Okay. This thing is so annoying. You know what I'm gonna do? This is so crazy, it just might work. What if I ditch this one? So I bought it today. Okay. That works. Okay. It's really small on here, but that seems to work. Okay. That means this one can get out of here. Right. Does it still say if it's recording? Good. Okay. Then I'm gonna get out of here because I think this one is like trying to keep up. This one's pretty old. It's trying to keep up. Okay. See how this goes. We're just figuring this stuff out. Ugh. All right. Looks like it's all caught up. Forgot what I was talking about. All right. So, you guys all good? Let's keep going with this output, shall we? Just kind of talking about it. Stop share. Okay. What's that over here? Start share. Share our studio even. Cool. She could. Can't seem to zoom in. Anyways. It's really small, but you have the same output, so I guess it's fine. But it's really small for me even here. So the residuals are going to have a standard error as well, right? And so that's just telling you the spread that you're expecting to see in your residuals, right? And so, and then if we go down to the multiple R squared and the adjusted R squared, they should be pretty similar for a simple regression. Once we get into multiple regression, I'm pretty sure we want to use the adjusted R squared. I'll check, but even looking at it, if I'm looking at an R squared, right, 72 versus 71, which one am I going to choose? I would probably, if I wasn't sure, I'd probably use the lower one. So I don't want to use the higher one and have someone come up to me and be like, hey, why did you use this one? That's not how good your model is. Right?
Sorry for this, but we have to consider adjusted R squared because that one considers the disturbances.
Yeah. Which is going to be more important for multiple regression.
Yeah, that's
yeah.
multiple regression.
Yeah, but we're in simple. It's 1x. Nothing crazy. But yeah, so for me, but just to have a guideline, right? If you're looking at these and you can't remember, I would go for the smaller one because it's easier to say, oh, I just wanted to be really sure of what I was saying, right? You can always kind of backpedal if you pick the smaller one instead of the bigger one. It also gives us the F statistic, which we'll have a look at in a little bit.
Would you say that R squared is not
it depends on the situation. So if I'm modeling something that I know is going to be really hard to get a handle on, I'd be pretty happy with the 0.7, right? But if I'm looking at something that I expect to kind of follow a good sort of line, like in this stuff, right? Mileage should predict price pretty well. I wouldn't be too thrilled with a 0.7, whatever. So it depends on the situation. We don't do hypothesis testing on the R squared, but we do hypothesis testing on the correlation. So we can test to see if the correlation is significantly different from 0. It actually ends up being the same as the t, right? So we can test if the slope is significantly different from 0. We can test if the correlation is significantly different from 0. remember the slope is built off of the correlation, right? And so, stop this, start this. We can also test the null hypothesis that rho is equal to 0. And this is just saying the population correlation. Oops, I should write correlation. Correlation is 0, right? So there's no correlation here. We know the kind of the rules of the correlation between -1 and 1. It's a numerical measure of the strength and the direction of a linear relationship, right? And so if we're saying that it's 0, well, that's no relationship at all. That's the same as, basically the same as saying, well, is there a slope here, right? And so notice that the slope B1 is R times SY over SX, right? It takes the correlation into account, right? And then the standard deviation of the Y's over the standard deviation of the X's. So testing the slope, you should get the same results as testing the correlation, right? The correlation is built off of the standard deviations of X and Y, and so they're all mumbo-jumboed here, okay? Today, we're going to talk about just 3 different ways that we can test the same thing, right? So as long as you pick one way, and for me, it's just running the summary of the linear model, checking my t, checking the probability of my slope, right? That's going to do the trick for me, right? If you want to test the correlation, fine by me, right? But or if you want to run the ANOVA, test the variances of the different models, it's fine too, right? So you've got options, but at the end of the day, they're going to get you to the exact same results, right? You're going to reject it or fail to reject it. And they are testing the same thing, right? They're testing, is there a relationship here, right? Can we say that there's something going on here, right? And so here, testing the correlation I was going to say should, but it will yield the same results as testing the slope.
Is that 5 or 6? That's 6.
Where?
B1.
B1 is R. Sorry, that's a lowercase r. Do you guys use capital R? Smaller? You can use either or. We just love having different notation for the same stuff over and over and over again. Yeah. Same. Yeah, I know. It's like somehow it grows up when you square it. Yeah. But then I've been working in a different textbook and they use capital R for the correlation, and I'm pretty sure lowercase r squared. Weird. So they also switch, but anyways, can't win. What you have to remember is we have all these different ways to test the same thing, because early on, right, people were just cranking out ideas. Hey, what if we tried this? Oh, what if we tried this? What if we tried this? Right? Turns out they all do the same thing, right? But now, we've got all these options. And so I thought it was confusing in the beginning, at least, right? To think, well, why would I need more than one way to test it? There must be something going on here, right, that I'm not understanding. But no, they all do the same thing. You'll have your preference. People have their preferences, right? And so being able to run them all and understand that they're the same, right? That's good. Okay. So let's have a look at the rest of this output here. I feel like I'm getting faster at switching over though, so it feels good. And it's keeping up, crazy. All right, so we looked at the summary of our model, and just because I told you that you can access the residuals and the fitted values, right? I wanted to show you a residual plot. And so you can plot, and you'll have to access the residuals and the fitted values by the name of your model, right? So mod1 $, but if you run that, now we're looking at the residual plot of this linear model. We're looking for random scatter around 0. So that's why I put the ABLine h equals 0. And that'll just add that line on there, right? So not really necessary, but kind of fun. You can look at the histogram of the residuals, right? Because here we're looking for constant variance, right? So no, well, we're looking for linearity, right? No, so random scatter, no kind of funneling out, right? We have this random scatter, constant random scatter. We don't have that many data points, so I'm not really concerned about these empty spots. There was going to be empty spots somewhere, so may as well be there, right? But as long as it kind of looks like it could fill out, then I'm not too worried about it. Okay. We also assume that our residuals are nearly normal. Looks good to me. Again, our main argument is going to be, well, here we have 30 data points. That's not a lot, right? If we collected more data, right, it would be safe to assume that they would follow a beautiful normal distribution. I guess you don't have to say beautiful, but it helps. I also threw on the QQ norm. QQ norm is the QQ plot for normality. For this one, we're looking for a straight line across the diagonal, and we can add the QQ line to have a look. The only real kind of concern is up here. We're a little bit more lenient in the tails. If we had something weird going on in the middle here, that's bad, right? But here, again, if we have more data points, this little guy and the histogram do the exact same thing. So you only have to do one of them, right? And it's just a matter of preference. I think for some reason, most people use this one. I also, it looks nicer, right? You can kind of look and say, well, they're on the line, so great. But also the histogram can look a little clunky. And so at least if we've got this sleek QQ plot, then that helps, right? And so, but it's whatever you choose. I like histograms. I think they're happy and whatever. And then, how much time do I have? I added in the county health data. That's one of those data sets that you need to do a transformation on. Okay. And so the county health, if we bring it in, well, one thing I wanted to show you that's not on here, if you want to look at all the different variables against each other, right? In this case, we only have 4, right? County Health has 4 variables. So what I'm going to do is I'm going to just use the plot command on the entire data set. So plot County Health, not specifying my X and my Y's, because this will be really helpful if you just want to get an overview of all the relationships. So if you run this, even with just 4 variables, it's annoying because we only need half of these, right? Here, county against MDs. So I think it's they're trying to predict the number of doctors based off of the number of hospitals in a county. And so the number of doctors against the county doesn't really make sense. The county must be listed as a number, otherwise it wouldn't do that. But the number of hospitals against the number of doctors, it's here, hospitals against county. So we only need the top half or the bottom half, whichever you prefer, right? And so I'm seeing a linear-ish relationship between hospitals and beds and MDs, right? Linear-ish. We'd have to play around with it a little bit, right? But when we're looking at the hospitals and MDs, this is kind of that classic non-constant variance, right? For very small number of hospitals, we can easily predict the number of doctors, right? But if there's more and more hospitals here, it's harder to say how many doctors there are going to be in this county, right? Because the spread is wider. So we would have to do a transformation on one of these things. And we can focus in on just the MDs against the hospitals. You can do the transformation and add it to your data set. That would be if you're using it more often, right? But when I'm just playing around with it, you can do the transformation inside the plot command just to see what happens, right? And so, and again, that's something that could bite you in the butt, because you might forget that that's what you did, right? And assume that that's what it looks like. But if you do the plot of the SQRT, the square root of the MDs against the hospitals, keeping the hospitals the way they are to start, we can look at this plot, and now all of a sudden we've got this pretty reasonable looking linear relationship. Oh, the last piece of code that I gave you jumps back to mod 1. I think I forgot to move it up to be with the mod 1 stuff. That's okay. You can just use the ANOVA command. What I'm finding is that most of the output in the textbook, so if you're reading the textbook, most of that output has been our output. It seems like the ANOVA output, either they've added stuff on, the totals is what I'm looking at, or they use Minitab for it. Because they said that for the output in the textbook, they use either Minitab or R. And I haven't used Minitab, so I don't know what the output looks like, but either way, we've got everything that we need here. The output in the textbook just has another column of totals, which would just be the total of the previous 2, right? We can figure that out. And so, cool. This F value, hey, we've still got it here, is the same as the one we had here, right? So we don't need to run this, because how we judge this F statistic is, okay, well, our model does a better job than just using the average, is essentially what's going on. But we'll talk more about that. Because I fear I'm out of time. Any questions? Cool. All right. So we will have lab this week, just no lab next week. Cool. No questions? Sort of a question? See you guys later. I'll stop this recording.
Bueno,